do in this talk is, so I've actually got basically two presentations that I'm going to deliver to you today and tomorrow. One of them, as you can see, the first one is essentially basic introduction to energy harvesting systems. And this is essentially covering an overview of quite a bit of material, but looking quite a lot at the mechanical analysis and the optimization. And essentially, if you look at an energy harvesting device, what you're effectively doing is you're putting some transducer, some electronics, possibly some energy storage, and you're wrapping it all up within some sort of box to make something in a volume. And inside that volume, as you've seen already, you'll have typically a moving mass, and if it's a piezoelectric device, it'll be probably a cantilever structure with a mass on the end. And of course, you've got then some swept volume. So there's a whole bunch of optimizations that need to be done to maximize the power density of these types of harvester devices. So I'm going to talk to you in this presentation quite a bit about how we maximize the power density and how we think about the geometry of the device. I'm going to talk about piezo devices, of course, because that's the main thrust of what we're doing here. But I thought, given that this is an introductory summer school, that I should probably cover other types of transduction as well. So I'll cover electromagnetic, electrostatic, and piezoelectric. A lot of this basic analysis actually comes back for work that I did during my PhD, which now is back when I had a bit more hair. And that's, so that was in, I guess I started some of the analysis that you'll see here in about 2001. So it's probably correct, fingers crossed, because no one's come and told me yet that it isn't. So, okay, so what I want to look at really in this talk is a bit of, you've probably seen quite a lot of this already, I guess, in the previous talks, a bit of motivation for energy harvesting, look at a little bit of prior work, see what the sort of benchmarks and standards are. Then I'll talk about the transduction mechanisms, as I mentioned. We'll cover piezo, but we'll also cover electromagnetic and electrostatic. Then this section, as I've just alluded to, on fundamental analysis and optimization. And I know that with Michael Lallard and probably also some of the stuff that Paul Murrell has talked to you about, you'll have seen a bunch of equations, you'll have seen how to analyze piezoelectric materials, but here I'm really concerned with, if I've got a specific volume in which I can place my energy harvesting system, how should I make up the volume in terms of how much mass, how much transducer, how much energy storage, all those types of questions that are quite important, because in many cases with energy harvesting, you've got to create something in a very compact structure. I'll talk briefly about system modeling and simulation, and again, I think that's also something that's been briefly covered a little bit, and I've seen you working on the LT spice models. Then I want to talk a bit about the electronic interfaces to the transducer, and of course, you've just done that in some detail with some simulations there for piezoelectric. I'll talk about the interfaces for piezoelectric as well. I'm going to introduce you to, I guess, ultimately broadly the same sorts of concepts there that you've just seen, but with some slightly different implementations and hopefully some nice animations of what happens in the mechanics of what happens in the circuit. So certainly now that Mikhail has gone, I can say this, but of course I'm being recorded, so if he's going to watch this back later, hi. The original explanations that I saw from that team, including Guillemard and various other people who've worked on this synchronous switched harvesting, when they first started working on it, I thought that it was obviously fiendishly clever because the amount of power they were able to extract was significantly better than other people could. But for the life of me, I couldn't understand what was going on. I couldn't see fundamentally why it was better. So I'll tell you my sort of insights into why the performance is substantially better with those types of power electronic interfaces than with the more simple interfaces. So that's what I want to do in this presentation. Then after that, the presentation I'll deliver after that is going to be really a sort of general introduction to power electronics and a bit more detail about interfacing the circuit to the transducer. And I think, again, don't lose sight of how much of this is a system, and it's important that you understand everything from the materials all the way through to the electronics that connects to this thing, because otherwise you won't end up with something that works very well, you won't end up with an optimized system. Okay, so I guess what we'll do now, I don't want to get into anything heavy now because, of course, you're probably very tired after a long day and you're looking forward to dinner. So let's just do the sort of goofy stuff at the beginning of the talk. And then it's a sort of light finish for you for the day. So just to tell you a little bit more about where I'm from. So from Imperial College. So this is actually a picture of Imperial College as it was probably getting on for 100 years ago. Imperial actually came out of the Great Exhibition, which was something, I don't know if you know, Victorian Albert, when Queen Victoria was Queen of England and Albert was her husband. Albert was really interested in science and technology, and he really pushed that. It was one of the things the Victorian Empire, of course, was very well known for industrialization. And as part of that, they had the Great Exhibition in 1851 in South Kensington on the land that is now Imperial College London and the Science Museum and the Natural History Museum. If anyone's been to that area of London, you'll know that it's full of museums and Imperial College, and all of that came from this great exhibition, which was basically showing off to the world everything that England had at the time. So there were various colleges that formed at around that time. In 1852, City and Guilds College Institute, which ultimately then became the College of Engineering inside Imperial College, Royal College of Science, Royal School of Mines. So all of these then merged formally in 1907 and became Imperial College. Since then we've had a bunch of mergers and we've expanded what we do in terms of medical stuff, so mergers with hospitals. And then in 2007 we formally left the University of London and we became a standalone university. You can see here that one of the things that's still standing from the original Imperial College buildings is this thing called the Queen's Tower, which is this here. This actually is electrical engineering. This is a big administrative block, and you can see that the architecture is somewhat diminished over the years from brilliant Victorian architecture to concrete and glass. We're known for, I guess, a number of people from college. Some of them I hope you may have heard of. Probably you've heard of Alexander Fleming for the discovery of penicillin. I guess Abdus Salam you probably have heard of. The one here that is, I guess, most related to me, not particularly personally, but this guy, Dennis Gabor, was actually in the electrical engineering department, so he's responsible for inventing holography. And there's our building. You can spot the clean rooms here because of windows. So that's probably the only clean rooms on the 7th floor of a tower block, I would think. A little bit about me. So I'm actually from Yorkshire. So even though I've been living in London now since 1997, actually, I've really lost my Yorkshire accent. But Yorkshire is here. This is so Leeds is the sort of big city close to where I'm from. I'm actually from a town called Huddersfield. That's the railway station in Huddersfield. It's quite grandiose. And then just a quick quiz. So what is Yorkshire famous for? So hopefully you all know Yorkshire puddings. And tea, of course. Rugby league is something that was started in the town of Huddersfield. Obviously, hopefully, you know, nice landscape, lots of countryside, a bit different to London. Do you recognise who these three characters are? This one might be the easiest. Something that happens in November. Guy Fawkes. So Guy Fawkes was a Yorkshireman, and I guess if you wrote down his profession, it would have been traitor. What about these two? This is definitely harder, but much more related to science. So there's a clue in this one, which is a clock. Harrison, have you heard of Harrison, who invented the first marine chronometer, which allowed us to do accurate navigation at sea? So he's a Yorkshireman. This guy here is the guy that is credited with discovering oxygen, Joseph Priestley. So there are some famous scientists from Yorkshire. Okay. Right, let me just do a couple of slides on the sort of overview of the topic, and then we'll call it a day, because, as I say, I'm sure you're all tired. So, original motivations for energy harvesting then, and I guess, well, sort of current motivations, to solve the problem of infinite power supply that could be required in certain scenarios where you can't tether something because you can't have cables, it's not convenient, and a battery is going to eventually run out, either through self-leakage or just energy consumption in the system. So there's always this sort of constant desire to have a perpetual power source available to make things convenient, reliable, cheap, etc. The modern literature in energy harvesting started significantly in about 2000. There are a couple of papers that predate that in the modern literature, I think 97 and 98 maybe. There are a couple of guys in the University of Sheffield in the UK, Williams and Yates, who did construction of an electromagnetic-based microgenerator. And that is kind of how I got started in this, because my PhD supervisor, who's also a co-investigator on this project, and I'm sure you'll meet him at some point when you come to London, Eric Gateman, he saw some of those early papers and he wrote a grant proposal, and that's how we got started working on this topic. So essentially, from about 2000 all the way up to now, the literature has just massively expanded on this topic. If you do a literature search now, and many of you in the early stages of your PhDs will be doing literature reviews, you realise that there are thousands and thousands of papers on this topic. When I did my first literature review, there were about 5 papers. It was a much easier task for me to do a literature review than it is for you. One of the things that makes it an interesting topic is because it is really very multidisciplinary. And I know that obviously, the individual ESRs here are going to be concentrating on some specific areas, but in order to make things successful, you'll have to be aware of the rest of the system, and you'll have to interface with other people and talk to other people in order to make something that works properly. So it is something that requires knowledge of devices, materials, physics, electronics. Within that, of course, you need to know some mechanics. A lot of people who come from an electrical engineering background seem to get quite frightened of having to do some mechanics, but it's not that difficult really. So my original motivation for this was to look at how you put something onto the human body and how you power some sort of perhaps implantable sensor. And obviously the benefits are obvious in terms of energy harvesting for an implanted device, because you don't want to have to keep doing repeat surgeries to replace batteries, and you don't want to punch wires through the skin. This was actually a very challenging thing to start looking at because the frequencies are so low, and we'll talk a little bit about this and the dependence of the output power in a harvester with the amplitude and frequency of the acceleration which is driving the harvester. There's a very strong frequency dependence. And so if you're looking at vibrations as a sort of on-vehicle environment, that you might be looking at vibrations in the tens, hundreds of hertz, perhaps into the kilohertz, if we mount something on the engine block, for instance, then actually there's plenty of power available. If you put something in a very low frequency environment, where you're talking about just a few hertz, then it becomes really very difficult indeed. Just to have a sort of brief overview in terms of the dynamic range of power and energy, the total world electrical generation capacity is around about 4 terawatts. And down at the other end, the sort of signal power that you receive on your cell phone is about 1 nanowatt. And of course, in between, we've got all of these different typical devices. I hope that many of you have a kind of feel for matching power to a specific thing. Something like the human heart takes about 10 watts. So people have talked about maybe doing, obviously, cell-powered pacemakers to be put in energy harvesting devices into the heart. That is something that potentially is possible. But if you wanted to have an artificial heart, for instance, where you had a pump that was actually pumping blood around the body, then power level of 10 watts already, from what you've seen in these presentations and what you will have read about energy harvesting, getting into the watts is impossible for small-scale devices. So what we're really talking about is things that are sub-watt, probably things that may be sub-milliwatt, possibly into the tens of microwatts, And we're talking, therefore, with energy harvesting about powering things of the order of wristwatches. And of course, the Seiko Kinetic watch is a very good example of a genuinely useful and working product that is powered by energy harvesting. And a sensor node typically takes orders of microwatts of power as well. So we're essentially trying to create something that requires the same sort of energy as a wristwatch, and we know that that is something that has been successfully powered by an energy harvesting device. But of course, what we're interested in doing here is to make things that are much more integrated, much smaller. There are a whole bunch of different potential sources for energy harvesting. Of course, what we're particularly interested in this project are the kinetic ones. But lots of people have looked at all these different options. Of course, light, solar cells, thermal with temperature gradients and thermoelectric devices, or some of the heat engines that we saw the other day, the Stirling engine, for instance. Harvesting ambient radiation, magnetic or electromagnetic radiation through induction or through far field radiation is something that people also look at in detail. And then in kinetic, really we're talking, of course, in this project about movement and vibration. But also in terms of kinetic, you could think about fluid flow, so you could think about a turbine. We've done some work in Imperial where we have a very low speed capable turbine that is meant to sit in air conditioning ducts and gather the small amount of power that's available from the low volume of airflow, or maybe high volume but very, very slow airflow going through air conditioning ducts to monitor the temperature, for instance. And the mechanisms that we're going to use there for kinetic are this magnetic induction, piezoelectric or electrostatic. And of course, the focus of this project is piezoelectric. But as I say, I think it's important that you have a bit of an overview of the three different mechanisms in order to be able to understand which is better and what the advantages and disadvantages of each. Why do we choose kinetic typically as one of the more common ways of doing energy harvesting? So the original reasons from my perspective is why I started looking at kinetic. Some of the other options here, just basically for the application I was interested in, weren't very good. So thermal gradients, if you want to look at that in terms of, as I said, my original motivation for this, for doing harvesting on the human body, thermal gradients are very small. On the human body, you're not going to be at, or your skin is not going to be at a hugely different temperature from your surroundings. If you want to implant something into the human body, then the gradients are going to be even less. The temperature difference between different parts of your body over very small distances that you might be able to put an energy harvesting device are extremely small indeed. If we talk about harvesting ambient radio frequency, that's also an extremely limited technology. If you want to actively beam power from one place to another, as you saw in my talk the other day, you can do that inductively and you can do it quite effectively. But it requires a dedicated source. You can do things in the far field. You can have a dedicated far field antenna and you can power something potentially at the other side of the room. But it requires a dedicated source. If you look purely in terms of harvesting with the whatever is available in the ambient, then the power levels, the RF power levels are very low. And as you saw, we're talking about nanowatt levels of power on the cell phone of an antenna. On the antenna of a cell phone, no. Solar, of course, is no good if there's no light. It sounds a very obvious thing to say, but of course, if you're putting something onto the human body, if you want to implant it, then solar is not going to be a sensible solution. And so what you're left with ultimately then is the fact that the kinetic probably is one of the most versatile ways of doing energy harvesting out of all of these possibilities. And that's not to say that that means that the kinetic solution is absolutely brilliant or is easy to make it work. It's really more a case of the rest of them even worse. So the amount of power that is available in many scenarios for a kinetic energy harvester is low, and that's why this is an interesting topic, because it's very challenging. And certainly I've heard several people say over the last couple of days that you're not going to be ever designing an energy harvesting device as a general type of harvester. When you look at a range of batteries to put into a product, then there's 4 or 5 different standard sizes of batteries. You've got AAA, AA, C cells, D cells, whatever, PP3s. And there's a small number of standardized batteries, and people design products around those standardized batteries. We're not ever ever, I think, going to be in the situation where we have 5 or 6 off-the-shelf energy harvesting designs, because we're always going to have to tailor it to a particular application, because the volume is important, the constraints on the volume are significant. The vibration characteristic that you're going to be powering this thing off is going to have to be tailored to every specific application. Is it a fixed frequency? Is it a whole set of frequencies? Does that frequency change over time? All those sorts of things mean that actually producing a small number of harvesters in the same way that a small number of battery types exists is not something that we can do. So we're going to always be designing something that's fairly bespoke. Seiko, incidentally, did produce a version of their energy harvesting watch using thermoelectric type devices. So the well-known Seiko energy harvesting watch is the Seiko Kinetic. So they did make the Seiko thermic watch. Didn't work particularly well, I think, when you have people with long sleeves. So if you had a short sleeve shirt, then this would work okay, because it would pull heat up from the body and inject it into the atmosphere through the face. But of course, as soon as you wear long sleeves and it's hidden under your sleeves and your jacket or your shirt, it's pretty well insulated, so the heat flow through the device is quite poor. So they only make this for a short period of time, but they still make the Seiko Kinetic watch. So we're talking mainly then about motion energy harvesting. Most of the devices that you will see are what we call inertial devices. And this is where you've got a mass on the end of a cantilever typically. So if it's a piezo device, that's typically how it's constructed. And the reason that you do that is because you want to have a single point at which you attach the harvester to the application. So if you think about the way that most electrical power is generated, it is not generated like that. Most electrical power is generated in this sort of scenario here. Here's a turbine holding a power station, and there is a large turbine which is effectively giving you a huge amount of power onto a rotating shaft. That shaft is then connected to an electrical machine, which is then basically coils and magnets, which is able to then give you a significant amount of power and at a very high power density. But the critical thing about and difference about the way that we generate power in this scenario to the way that we typically generate power in energy harvesting is that we're basically here able to produce a massive force, because we're interested in the force between 2 points that we can grab hold of. In this case, we're putting torque onto a shaft, and the rest of the electrical machine is literally bolted to a concrete floor. So you can get a huge amount of force between the stator and the rotor of the machine, because the stator is bolted to the floor and the rotor is bolted to the shaft of the turbine. Now that requires you to grab hold of this power generation system at 2 points. You've got to grab hold of the stator, you've got to grab hold of the rotor. Now in an energy harvester, that's typically not what we would like to do. We don't want to have a relative movement between 2 points that we have to grab hold of. We'd like to really just have one point where we hold the device, and then if we shake the device and there's a vibration, then it generates power. And in order to do that, to get a relative movement at that point, we have to rely on inertia of the proof mass. And that is fundamentally limiting in terms of the power density we can achieve compared to what we achieve with this solution here, where we've got a direct force that we can apply directly onto a transduction mechanism. So the sort of equivalent here of this direct force approach is this inertial approach, which we use in harvesting. And you can see here the basic principle here. We've got, in this case, a torch that you can shake, and it will generate a little bit of power. Actually not very effective, this, but I've got one in my office. There's a magnet here that moves up and down inside the torch. There's a coil, as you can see here, and you get a little bit of power. Not very well optimized, but it kind of proves the point that actually the amount of power that you can get, or the density that you get from this type of device with a single attachment point is very, very different to the power density that you get where you can bolt them to the floor and bolt something else to the shaft of a rotating machine. Okay. So essentially this is the sort of direct force type device. One side of it is bolted onto something, the other side I can grab hold of and I can move. And that means that I can produce very large forces. If instead of having this device bolted onto something and a handle onto grabbing the relative moving part, if this is all encased and all I can grab hold of is this box, then I'm relying on the inertia of the proof mass to do the relative motion. And that's ultimately what is limiting the power that I can generate with these devices. Is that a reasonable time to stop? Yeah? Okay. All right, thank you very much.